concepts, and you have to be able to use them at least a little bit. What time is it? It's time already?
It's 18 after. It's time.
Okay. And
there is no queue. Who's the call?
yeah.
No question times. Let me write the administration.
So last time we saw a lot of things, especially the key concept of martingales. We saw that a martingale has three properties, two that we almost always forget, but that are very important. That is, they are L1, and they're adapted with respect to the situation. It is, they depend on the information we have, not on the future. And knowing the past, the average of what I can find is MS. It's the information that I have. So, as we said last week, we do not gain anything. It's the idea of a fair game. Then we saw quickly the idea of the stopping time, and we'll make an exercise on it. And we saw the Brownian motion, which is the example of a continuous martingale. The Brownian motion starts at 0. The increments follow a Gaussian law with variance t minus s, and the increments are independent. We forget what happened before. And finally, we saw the Dooth stopping period. That is, if you have a martingale under some assumptions, let's forget about them for today. If you have a stopping time tau, you can stop the martingale, and expectation of this martingale at this stopped time is the expectation at the first time. We will practice that today. But first, let's take the random walk that we talked about yesterday, last week, sorry. So we have some extend. Extend is just a jump of 1 or minus 1. So you gain 1 knob or you lose 1 knob, and you keep on betting. And SN is the total results after betting n times as well. Okay? The filtration is the one spanned by S0 to SN, and which of these are stopping times. So this is not completely trivial, it's not trivial. So you have to say which ones in these 5 stopping times depend only on the present and the past, and not on the future. So typically you look at the event T1 is less than n, and you want to say that this event is in right? So here T1 is less than or equal to n. You see that well, it depends only on n. Okay, let's call it n. Sorry, n. T1 is less than or equal to n means that Sn is equal to 42 for n before n. So this event here is exactly equal to Sn is equal to 42.
42 is the particular number from Hitchhiker's Guide.
Sorry?
42 is a particular number from the Hitchhiker's Guide.
Yes, exactly. I needed a number. It's a fantastic book, of course, if you haven't read it already. Yeah, there exists n less than or equal to n such that Sn is equal to 40. And you see that this exactly depends of the Sn that are less than or equal to n. So this is measurable, this is adapted. This is a stopping time. Okay? Now, another one, it's more tricky. You see that it's the exact same, except that if m is less than 42, well, this is the empty set. This doesn't exist. There's no problem. But if m is greater than 42, then we have to find the n if there exists an n such that Sn is equal to Sn minus 42. Okay, and if this exists, it depends on Sn, n less than m, and Sn minus 42, which is still less than n. All right. So this is also, sorry, here it's not, because it depends on, imagine that n is equal to m, is equal to 42, let's say, but it depends on S42 and S84, which is completely in the future, I don't know it. It's not a stopping time. This one is a stopping time as well, because this one, yeah.
Completely in the future, but how do you know when this future starts?
Exactly, yes. So here I should look at one example. The event.
Because as I see between T2 and T3, okay, I understand that if Sn is equal, you know, then Sn minus 42, it's okay.
Yeah.
But for T3 and not T, why you do not know?
Yeah, so we have to take an example. So let's take this even, T3 is equal to 0. T3 is equal to 42, sorry.
Yes.
So it's equal to the step S42 is equal to S40. 84. And you see that this does not belong in F42 because this is you only lose the information about S0, S1.
I don't understand why 42, why F42 is related to T3.
This is whereas we want to know that this is measurable at the time the data happens. T3 is 42. So it has to be 42 measurable because this is the event T3 equals 42. So whatever T3 is equal to must be measurable at that time.
Again, I don't understand why T3 is equal to 42. But
because I can also, I could have
minimum, what is it? T3 is minimum, yes? So,
okay, it's because okay, this one I can.
no, it's okay. So, but the definition, the first word before the parenthesis, it's minimum?
Yeah.
Okay.
It's minimum. Yes, sorry.
No.
So this one is also measurable because T1 is measurable, and it's the exact equivalent of the space. Similar. So it means that after the time T1, which is adapted this time, then Sn is equal to 0. Well, you can won't do it, but you can prove that it's fine. And this one typically doesn't work because you have a maximum here. So you take information that is too far away. So if you want to prove that this one is not measurable, I suggest that you look again at T5 equal to 0. And this event depends on information from 0 to 42. This is not a student. All right. Now let's quick exercise on martingales. So we already proved that this is a martingale. We saw that Sn is less than n. So in particular, it's n1. It's less than infinity when you take the expectation. We saw that it's adapted. This is also fine by definition. And expectation of Sn plus, okay, let's do Sn plus 1. It's the same. Sn plus 1 knowing Fn is equal to expectation of Sn plus Xn knowing Fn. This is equal to both of these are measurable. So I get Sn. And Xn is completely independent from Fn. Right?
Yes.
Yes, Xn plus 1, Xn plus 1, that's one. And we have expectation of Xn plus 1. And this is 0. All right, this is a multi. And we'll just use the second point. That is polynomials you can actually, from a martingale, you can transform it into another martingale if you take polynomials of martingales that are taken in a clever way. So then, for this one, we have expectation of Sn plus 1 squared minus n plus 1. So we have expectation of Sn squared minus S Sn plus 1 plus 2 plus n plus 1 squared minus n minus 1. Now we have Sn squared. For this one is mirrorable, so we have plus 2 Sn expectation Sn plus 1. These two are independent. And finally, expectation of Sn plus 1 squared minus n minus 1. Now this is 0. This has values in minus 1, 1. This is 1 is squared. And you find Sn squared plus 0.
I'm sorry, I'm lost so quick from answer. Expectation Xn plus 1 squared. Why is 1? Once again?
Because Xn is take values in 1 or minus 1, almost surely.
Okay.
So if you square it, it's always 1.
Plus 1.
Yeah, that's plus 1 minus 1. I have minus n, and this is exactly what I wanted to do. Okay. Let's go back to this uses the same technique. If you want, we can discuss it afterwards. Right. We stopped at the Brownian motion. We gave a definition. We gave a few interesting properties, especially these ones, but I will recall. So of course we have WT evolution, whose variance depends on T. We still had the expectation of the Brownian motion is of course 0. I'm just writing, and I just use this. The expectation of WT squared is T. And most importantly, the expectation of WS is the minimum between T and S. We saw that W has a alpha Eulerian multiplication with alpha logs 2.5, but not 1.5. We saw that it can be, we'll assume that it's continuous from now on. And finally, there's we talked about the fact that W is nowhere differentiable. Okay, so if you want, if you see, we consider as derivative of the Brownian motion, it means that we're talking about distribution, not a real derivative. All right. So that was next week. Now for this week,
What was the last one again? Only on W.
it's
Minimum.
minimum.
So this is WTWS.
X.
And is this wedge, is it a minimum?
Yes. So, of course, we want to know what the Brownian motion is in RD, especially for application. So, a Brownian motion in RD is a vector whose components are Brownian motions, independent ones. Independent Brownian motion. And now, if you want to draw a Brownian motion on your computer, it's actually not that hard. numerical consideration of Brownian motion is done following way. So we take a time interval 0t. We find its utilization and h equal to t, or n, where we have n plus 1 points and h is the step size. And we give ourselves psi 1 at the end, independent Gaussian vectors in order. So independent with psi I and 0 identity. And then we find W plus 1 equal to Wn plus square root of h and W0 is equal to 0. So that's what I showed you at the beginning of the course. We begin at 0. We take a Gaussian and we make a jump. We take a Gaussian and we make a jump, and another jump, another jump. It can be huge, it can be very small. And when h goes to 0, then you converge to Brownian motion in a way that we'll see later at the end of the course. You can also see that this process is a discrete martingale. So it's not crazy. This is a martingale that approximates Brownian motion with a continuous martingale.
Yeah, great question. If you start by let's say you have a course path like this, and then you want to refine it, is there a decent way of doing this? You know that it should go from there to there, and it's a decent way of refining it to be a Brownian motion in between.
What do you mean by refining it?
I mean, you don't take the steps there.
Yeah.
Is that we have these points, we want to have these peaks, but we want to fill in between the points with something nice that is also Brownian motion.
Yes, this is very hard. It's very hard. It's called the Brownian bridge. I hope that it exists, but for the moment I didn't find any proper algorithm to model a Brownian motion knowing the starting point and the ending point. This is very hard because you need to use Gaussians knowing that you have to finish here.
Mm-hmm.
This is not trivial.
Isn't the same problem that to find the geodesic starting from the point in some direction is easy, but to find the geodesic that connect to points, it's almost impossible. Only knowing very much.
I'm not sure because in that case, at least if you are in the same normal neighborhood, you use another shooting that
But I do not know the medical stuff.
If you go to shoot the cannonball and you don't hit completely, turn it to the right. Shooting things, but here it's more difficult.
Well, I worked a bit on it, and you can imagine some methods, but you never know that. You can imagine something that looks like a Brownian motion in between, but yet if you take the set of all possible Brownian motion that you create this way, it will not have the result. So this is actually a really good question. If you have an idea, I know thousands of people interested in this, but I don't think this is easy. I think this is almost impossible. We can talk about it. Anyway, composition, something that we can observe. We take WT, the Brownian motion, and then we'll modify it a little bit. So we have the homogenization property. It is WT plus H minus WT is a Brownian motion. So if you I don't know if it's way better or not, but if you begin again here, you get Brownian motion. If you just take the difference with W of H squared. You begin at 0, you get the Brownian motion. Okay, then symmetry minus W of T is a Brownian motion. And we have a scaling autosimilarity property. So lambda W of T over lambda squared is a Brownian motion. And I emphasize for lambda greater than 0, you cannot go backward. This does not exist. The Brownian motion never goes backward. And finally, the inverting time property is T multiplied by W 1 over T is a Brownian motion. This one is not easy. This you can check. Just take the definition.
T 1 over T.
T 1 over T.
So it's homogeneous in both cases.
Yeah. Wow. Yeah, exactly. Wow.
For the first one, we fix T and the specification is in H.
Yeah, right. I should write T0 first.
Makes sense to distinguish. The third case, T is the variable, so
yeah.
Lambda is not the variable.
Lambda is space, T is in space, T is always a variable.
Yeah, T
is actually the variable, so this is the coefficient from the very important case.
Two different meanings.
Yes, the third and fourth case have different meanings. The third case, T is the variable, it's not part of the scaling. But in the fourth case, the T that you're multiplying by up front is part of the base of the variable.
But can you write it a little bit more extended?
We can prove it. I think we should prove it. So
this is not surprising me. The third, fourth one is the only surprising one.
But he is not the same as in the third. He's cheating.
So this one, if you really want to prove it, you remember when we talked about the characteristic function, this Fourier transform, then you should use it and take to find that it actually follows the Gaussian step, and then everything should be okay. But let's prove this one maybe. So I will not prove everything. I just want to prove that lambda T over lambda squared goes on n 0 T. For this, we know that it's equal to lambda multiplied, it's equally low, lambda multiplied by 0 T over lambda squared, and if you multiply a Gaussian law by constant, you just multiply the expectation by lambda and the minus by lambda squared. You get the answer. Once that's not enough, there's a criterion that will not see that exactly stated. So this one. Yeah, let's forget about it. This one is hard. This one is definitely hard. It's not straightforward.
But then the third one is also interesting. I think that's essentially how you show that the Brownian motion has also dimension 2. It has its scaling invariance.
Yes, indeed. And when we talked about these Brownian bridges to fill the gaps in between, the first attempt to solve this kind of problem was to say that you take the Brownian motion and you scale it using this property so that it fits and it reaches the good points. Sadly, it doesn't work. This scaling property is the one we observed at the very beginning of the course when I used my mouse to zoom on the Brownian motion and we kept on seeing the same exactly. That's this property.
Some similarity.
Yeah. Autosimilarity. Yeah.
The fractal properties, the lot of fractals.
Yeah.
Just agree that the fourth property is a reversal of the interval as well.
Say again?
Can't you just say that?
I see that everyone is confused with this property. It's fine. We won't use it. We will try to put an explanation about it in this.
So any cube of the Gaussian motion has Hausdorff dimension. What do you want to say? You mentioned about the times.
The Brownian motion has absolute dimension too.
Any curve in the Brownian motion because they
Probably
have
with also measure excess of in the measure scale.
because you have different
Probability, but almost sure.
All right. The final property that I haven't put here is that if you take W M W into two stochastic processes such that MT is equal to W squared minus T. Remember the exercise that we saw a minute earlier. Then W is a Brownian motion, even on if M is a Martingale.
Why MT?
WT squared minus T, we just define a Martingale like that. And we saw in the exercise that if W is a Brownian motion, then this is a Martingale. This is the exact same proof. But if this is a Martingale, you can actually show that W is a Brownian motion. So we really have a link here.
Is it some sort of criterion to be the Brownian motion?
Yeah.
Yes.
Yeah. Because then we will.
So from any martingale, you can somehow recover the Brownian motion.
Yes, almost, yes. We will, because you see that I talked about with examples of martingales that are discrete, right? But almost no examples that are continuous except Brownian motion. There is a reason for that. So, stop teasing you. Just a last property to use everything that we defined. We define A is the infimum of the positive signs such that the Brownian motion reaches the bound A. We just look at the time where this Brownian motion hits for the first time value A, and this is TA. This is the sloping time. So TA, the proposition says that TA is finite, always fully. This is called the recurrence of the Brownian motion. Whatever value you will hit it, the Brownian motion will hit everything. And for all A less than 0 and B greater than 0, we have probability that TA is less than TB is equal to B of the B minus A, and the probability that TB is less than TA is equal to A of the B minus Let's prove it quickly. Not all of it. This is hard. So A in R. A in R, yeah. And this part we'll just talk of Brownian motions in R. Not yet. Right. So we will assume that this is true. So we have two events. We know that the probability of TA is less than TB, plus the probability of TB less than TA is actually 1. Because we are finite motionally, so this represents all the cases that we can have. Of course, you can add less than or equal to, but it has measure 0. But literally, W of T cannot have both my values A and B at the same time. Okay, then we will use the Dup's theorem. So we consider the martingale W, the Brownian motion, evaluated at time double T and stopped at time T, the minimum of T, TA, T. I can't just take minimum of TA or TB because then it doesn't satisfy the hypothesis of the Dooms theorem. So it's a trick. We just take the minimum with T. This way, this thing is bounded by T, and we can apply the Dooms theorem. Just forget about it for a moment. So we go down and we apply the Dooms theorem. What we have is that the expectation of WT minimum TA minimum TB is equal to the expectation of W0 equal to 0. Okay. Now we have an integral parameter T that we would like to erase, dominate the convergence as with integrals, and we take the limit in T. And we find the expectation of WTA in T. And this is a dominated convergence. All right. Now this expectation, we can actually compute it. T expectation of WTA in B is equal to, first, let's assume that we are in the case where TA is less than TB. Yes. And then we have WTA plus the probability that TB is less than TA, WTB. This is just A, and this is just B. So I have two relations, this one, and probability of TA less than TB multiplied by A, plus probability of TB less than TA multiplied by B is equal to 0. That's my second relation. And when I put both of them together, I exactly get that. So this is the kind of application that we have for the Dooms-Stopping theorem. It's not useful per se to understand stochastic integral and everything. But if you want to go a bit deeper, as we do in this course, for studying stochastic integrals, it's important to understand that we have to stop the case, because then they can explode, we cannot prove anything. And for this, we'll use some stopping theorem, such as this one. Okay. And just to comment about this thing, this property here, the recurrent result that comes from the recurrence of our motion. The recurrence of our motion says that we reach everything, the Brown motion is subjective in a way. This is in the low momentum, so just so you know, it has a name. What time is it now? And yeah, I think we will start here.
What is the assumption that you use for any of the Dooms theorem?
The Dooms theorem that this time here is bounded. It's bounded by T. That's why I put this T here.
Because you don't know if there are no T and T.
No, we don't know, but it's not anyway. Usually the Dooms theorem, you put this T here. This way you can apply it, and then you apply dominated convergence to get what you really want.
And if you have so this assumption, can you satisfy one of the two others?
The what?
One of the two assumptions for playing the theorem?
I don't think think so, not in this case. That's how we do it. And I think we'll just take a small break here to eat some pizza, nicely prepared by Francesco. And then, yeah, question, is Didier coming or not? Because he wanted to see, okay, because he wanted to see the construction of the Brownian motion, so I can postpone it a little bit, but not too much. Try to finish the chapter on stochastic processes. Yes. So two possibilities here. The first one actually build the Brownian motion and show that it exists because I never showed that it exists.
This square root exists, square root of 2 exists.
Yeah.
But why Brownian motion does not exist? It's a philosophical question. Do not hear me. I'm trying to say.
I can't see it.
You know, it's the end of the game. Brownian motion nothing exists.
You know, we have this French teaching exam with l'agrégation, and you had to present the development proof. And one of these that was quite classical was to show that independent random variables exist. Like you can create a set, an infinite set of independent random variables, and it's really hard actually. It's really hard. Like
uniformly distributed.
Yeah, because you keep on introducing new things, but we still don't know if all of this exists.
You
So in that
stuff with a Rademacher function.
yes, exactly.
And this is not. Yeah, it's not easy.
It's not easy at all. Anyway, so the first construction is with a random motion. It's exactly what we saw up to now. We take a time interval 0t, a discretization, Tn is equal to Tn, I will write delta t. So everyone knows. We take a list of easy random variables with probability of yk is equal to plus or minus square root of delta t is equal to a half. Okay. Blah blah blah. We consider xn is equal to y1 plus yn.
And then you want to create d-dimensional Brownian motion.
No, one.
One dimension.
Then you can just create another
No,
one.
no, I do not want d-dimensional. I want to have one dimension.
It's 1D. 1D. Because it's easier. So here you can see that the expectation of xn is the sum of the expectation of each, which is 0, because it's just square root of delta t with probability 1/2 and minus the square root of delta t with probability 1/2. The expectation is 0. Then you see that the expectation, the variance of xn is actually n times the variance of each, which is delta t. This is what I call Tn. Now, as I did before, so we have the value of xn at the times Tn, but not on the rest of the interval. So we just interpolate them with a different function. That's what you do. You get x1, x2, x3, etc. And we interpolate them like this. And we get the function x of t. With a precision given by the x delta t. Okay. Then you can see that the expectation of x of t is still 0. I need another chart. We have an issue. What do you Joe?
I will be.
I can hear you. I have a weird shape that fits the fine. Okay. And then you can show that the variance of x of t is equal to t plus
So X of t is interpolation of
Yeah, the
linear
linear
interpolation
sure.
between each.
That's enough. Then we have an XD converted in low to Brownian motion. This is not easy, but something we can do at our level is to use the central limit theorem to see what's happening. So we have xn of the Tn equal to y1 of the square root of delta t, yn of the square root of delta t, divided by the square root of n. We just rewrote everything. So this is working. Yeah.
Yeah, should be square.
Yeah, then it's fine. Here, this is exactly the framework where we can approximate and where we can use the central limit theorem. So we know that it converges when you go to n01. So if you multiply the square root of Tn, you have xn approximately n0. I simplify everything because this is not the most important construction, but this is the idea. You just build an interpolation by adding motions. This is not how Brownian motion was actually created in the beginning. The first construction actually uses some isometry, and it was done by Wiener. Hence, me writing all the time W of t for Brownian motion instead of BT. BT stands for Brownian, and W of t for Wiener. This is Wiener isometry. And here is the idea. We have, we just work on 0, 1, and we know that the integral of the indicator of 0t multiplied by the indicator of 0s. This is equal to the minimum of s if I integrate from 0 to 1. Right? So I just, this is, if I work in L2 or 0, 1, what I'm actually doing here is that I'm just computing the scalar product, let me write it like this, between the indicator on 0t and the indicator on 0s. Right? But we know something else. On the other hand, we have that expectation of WT, WS is equal to the minimum between S and T. It is the exact same thing. And here I work in L2 of omega. Okay, not omega. Omega is the space of randomness.
Okay.
Yeah. So the idea of Wiener is that we have the same thing here. There has to exist an isometry that tends one to the other, as we just consider a scalar product here, and this is also a scalar product. It's just, I mean, writing the same. Here it's an integral, and here it's an expectation, which is the same thing. So there has to exist an isometry from one L2 space to the other.
And something from on the interval to the geometry measurable space. I mean, okay, great.
Okay. Asking says
Okay,
something
two
like
L2 functions, so okay, two L2 spaces.
Yeah.
Between two L2 spaces.
but there should exist an isometry.
The spaces. Because they are isomorphic.
Yeah, but here he wants to find a particular one. That,
You want to have not isometries, you want to uniformity, that is something.
Yeah. That's an isometric psi that goes from 1. Such that a psi of indicator of T is called equivalent. Now, the good thing with Hilbert spaces is that we have an orthogonal basis. So you say, yeah, this is bad, but it's fine. An orthogonal basis. And psi, psi n is equal to psi of en. I send the orthogonal basis to another one.
What is silent orthonormal basis in the space of A101?
Yeah, so
what is it?
So this one is the orthogonal basis in L201. So this one, if psi is an isometry, should be an orthogonal basis in L2 of omega.
What is E1? En?
En is the orthogonal basis in
Yeah, I
L2.
know how you define it.
Any orthogonal basis.
I know, but this is triviality. What you write is a triviality.
Yeah, it is.
Okay. I thought that you start to make it.
No, I
take this and create orthonormal basis.
No, because I don't have to. I don't have to. Now the assumption would be there is that this is actually a standard version of the Bible. Or whatever. And what I should have is that the logic can be decomposed with respect to my orthogonal basis as a sum of psi n, the indicator from 0 t, scalar product with En. And this series, as we know, should converge in L2. And then that whatever, if you take any orthogonal basis, you take the isometric that sends it to psi n, which is indeed if you take a collection of standard Cauchy random variables that are independent, this is indeed an orthogonal basis for omega. Then you get this. And this series for any En, it works. It has a low Brown bush. The main problem here is that it converges in L2. And I want to tell you, I want to tell you the validity. I cannot accept it to be only in L2. The trick here, and the real, and the winner also goes, but it's
and there is also, sorry, I'm lost. So with this psi n,
yeah.
with how do you define this psi n?
So you can prove that L2 omega is an orthogonal space, and you can take an orthogonal basis of it that is given by a collection of independent random variables that are functions. And you see that they have to be.
Okay, so those are the psi n's.
Yeah, you choose that. It's okay. Now, we finish this. The main problem in Wiener was to actually give a sense of convergence that is the standard one. You want this series to converge uniformly.
Can you stop a bit? So I understand that W, you write the position to the basis, with the basis psi n, but why coefficients are calculated in this form? Why is it product between En and so I'm slightly from the general perspective.
Okay, let me do it properly. The indicator 0 t is equal to the sum of
some coefficients by
En with square product indicator 0 t. So yes. Okay, and then you take 5. Well, I will write it anyway. I should have written it. And then when you take 5, you obtain 5n, how I define it, within. Anyway, Wiener found a particular choice of En that makes it work.
The idea actually the other way around. So you psi n, you know what is this.
Exactly.
And actually you want to find the orthonormal basis, that range of that one, under that kind of isomorph. Yeah, okay.
Yeah. I mean, there always exists. Like
so of course it exists, but I'm trying to understand the construction. He knows psi n because this is a standard Gaussians.
Yeah. And
he knows that it's orthonormal basis.
Yeah.
And he wants to find the image, what kind of basis in H01 exists.
He wants to find any that makes it converge, that makes the series converge.
But in L2C, I guess. In L2C, 01.
Well, it always converges in L2.
In L2, of course, but I mean, I guess you want to converge in L2C, 01.
Just the usual convergence of series.
I mean, okay, you have to you have two variables, omega and type t.
Yeah.
So, but when you say converges in some space, which space? For me, I think it's L2 on omega is values in C01.
Yeah. Oh, that's what you meant by L2C.
Yes.
Sure, exactly. Yes, I agree with you. Exactly. So if we take, I had finished. If we take a particular choice of n, series converge uniformly. So in L2C, as you said. And what we have is that I just give it to you. It's psi 0 times t plus the sum from n is equal to 1 plus infinity of psi n over 2 sinus of phi n t divided by phi n. But it's just a choice. You can prove that this is actually a Brownian motion. You can build it. This series converges uniformly. And the funny thing here is that if you try to derive this, then you get cosine of phi n t, right? And this absolutely does not converge. Okay. If you try to derive in t, so to get wt dot, you get a series that does not converge.
Because you get cosines, you will not have this pn that will divide.
Yeah.
It's single. Yeah, okay, for the Fourier transforms or whatever, this is the essential that you have this kind of basis.
Yeah.
Sine divide, sine x divided by x. Okay.
Okay.
Otherwise.
So there are other constructions, and these are especially interesting if you want to consider SDEs, because then if you want to build a Brownian motion in space and time, you have to think about what kind of thing you want to obtain, and there are different ways to do this. We will not talk about this in this course, and I don't think so. But building the Brownian motion is a good question. Now for the regular acute trajectories. All right. So we begin with the definition. And what I'm going to present here is a bit technical, but we have to do this. It's very important. So we take a function from AB to R, which is not continuous or anything. This is just a function. We take a partition R. So this is known to A, then T2 equals something, and T2 is equal to B. We take just a partition of AB, and we write variation with respect to partition phi of f is just the sum of f of ti plus 1 minus f of t. So if you recall one of the first courses, the very first course actually, done by Gianmarco, we talked about that, to build the Riemann integral in a systematic way. And then we'll consider a new thing, which is quadratic variation, d by 2f, which is the same thing, so because it's at the end. Okay?
Sum in this way.
So this is sum of the same thing, and this is
Sum of the squares.
yeah, the sum of the squares.
So what do you call the second one?
The quadratic variation.
And when it's finite, what do you call the function space? Sorry.
It exists.
Because I use that, but I didn't know the names. Quantum quadratic.
Yeah, there is BD functions, BD2 functions, and so on. No?
So this is not bounded to variation.
No, it's not.
Will you say this or?
No?
Will you say this? Will you
No,
explain
no,
the
I
difference?
agree with you.
Will you explain the difference?
No, you can talk about it.
So the types of partnerships, the way.
Okay, no, I say it here. Okay. So the total variation of f on AB is the limit d of f. The limit when the size of okay, it's premium, so it's this way. Premium on phi of d phi of f and the quadratic variation is e2 of f. Suppose that this sign is different to the limit when the size of the partition phi goes to 0 of e2 phi of f, where this size is simply the supremum between pi plus 1 and
Stupid question. Why limit exists? Because you need monotonic sequence, or why limit exists?
it does not exist in general, but we always consider it for it will.
It should be in sum.
Yeah, but if you consider the supremum, it's not the same thing.
It's not
I'm just saying that they're going to understand. If it was in soup, then I could understand that. Where is three?
No, I never asked myself these questions, but
No, but you write limit and limit. That's
true. Yeah, there's not exist in general. It's true.
It can be infinite. It's monotonic. These are monotonically increasing.
That's what I'm asking. You make
As-
some monotonic increasing sequence, then I agree. And it's not a problem for me to have infinite limit, but in general. Okay, great. Go.
What's here to be said is that V2 pi here is just a supremum of across all pi's of the same measures. This is what you're looking for, two variations.
We'll just use it in a way where it always exists. Anyway, sorry. I don't use the definition of the supremum because it's not the same thing. So if f is continuous and p of f is less than infinity, then the quadratic variation of f is 0. It's always 0. So a way to see this is take directly the definition and e2 pi of f here. Yeah. So we can just bound one of the two absolute values by the maximum of f of v minus f of u. So it's less than the maximum of f of v minus f of u. For uv, for v minus u less than the size of I, multiplied by v5. Everyone agrees with this? I just bound one of the absolute values in these, and then I'm left with the sum of blah 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 with the square. I just get this. Okay. This as f is continuous. When the size of I goes to 0, it goes to 0. And as so, yeah, the Brownian series it's not enough because I have a bias here as well. So I should first take this. I think this is less than v of f. And then I can take the limit to this one.
So the second, not the second page.
It's not.
It's not.
The second variation is this property repeat process.
It's behavior. So if you have a function of bounded variation, two variation is equal to 0.
Yes. Okay. That's what is proving. This equivalent variation doesn't necessarily exist. It doesn't have the sort of properties you get from variation.
I can check on the internet without the properties of space. I really never go to that because I don't use it in my research, but I should know.
Bounded variation implies a function such as it doesn't really underline. You have a product of bounded variation, it's not a bounded variation.
Okay, so you guessed it. If you take a function that is regular enough, I see one, then d pi of f is for any pi. This no, not df is the integral of the absolute values plus derivative. Of course, it will not work with ground motion. You can see that f prime does not exist for ground motion, so something annoying with the key here. Okay. This is the most important thing here. If WT is a ground motion, then V2 of W is equal to G. Yes. Capital T. Notice that there's no expectation anymore. There's no randomness. It's just V2. It's always T. And is infinity.
That is included continuously with the distant one is not rectifiable. Repeatability is bounded variation, it's the same, it's just two different words that used from two different.
That's why you talked about repeatability.
Yes, repeatability is bounded variation.
Okay.
On the interval. Yes.
We should have talked with BV then.
No. Originally it comes from BV when you go to the several spaces. Then it has more.
Okay.
Originated this with the because the notion of repeatability in variable spaces is much more.
Okay, I didn't know.
They deviate from one variable.
Oh, I saw real analysis course where they focused not on smoothness and everything, but they worked mostly with body variations. And it changes everything because, okay, it's a bit more technical, but makes sense as well. It's the same, almost. Anyway, so we won't prove it because this is exactly the result where I said we need to move again the lemma and blah blah blah. We'll just prove it weakly, like there's a lemma to prove it. We'll prove the lemma. So let us prove. Then there's and to obtain this almost short thing here is annoying. We won't do it. So let us prove that this is true in expectation. So V2 of W minus T is equal to 0. And expectation of V2 W minus T squared is equal to 0. We needed to prove it. Again, usable identity lemma, Markov inequality, if I remember, and that's how you obtain the almost true conversions. So for this one, we can write it for a proper partition. So we have V2 by W minus T. Can rewrite it with the telescopic sum. That's the sum of W Ti plus 1 minus W Ti squared. Actually, it's different. And then we subtract Ti plus 1 minus Ti. From I is equal to 1 to yeah, I said P, you can say P. Everyone agrees with the telescopic sum, it's fine. Now,
0, I from 0.
Where?
I from 0.
I said 0, I know, maybe. Yeah, let's put 0 is here. With T0 is equal to 0. We just write it this way, and you see that the expectation of this is exactly 0. So this is equal as expectation of WT minus WS squared is equal to T minus S. Remember this? Then the expectation of all of this is 0. Yes, something's here. I just rewrote T with K plus 1 parentheses.
Oh, now.
Okay. This time you can wait for hands, and I will understand. Okay.
But you're not going to prove that the link exists, you just
no,
suppose. Okay.
Because I don't want to use too much that I can give a reference. It's not that hard. I said we wouldn't use simple identity lemma too much. So thanks for my box. Now we have W minus T squared. So we have the sum of R equal to 0 and 0 to T minus 1 of W fourth. Minus 2 the sum of T plus 1 minus 5 expectation of W T plus 1 minus W T squared, and then plus So just so this we know that it's exactly equal to T plus 1 minus. And this one we saw it only once, but the fourth moment of the motion law is 3 times the volumes squared. We have 3 minus 2 plus 1. The sum of Ti plus 1 minus Ti squared. Exactly. I know how to compute 2 times what? 2 times. No, it's fine. This is fine. It's not fun. No, it's fine. It's fine. Yeah. This is this. I from 0 to 2 minus 1. And then here we have the quadratic variation of a differential function. So it's just the integral derivative. Why is it 0?
Quadratic variation of value.
Yes, exactly. The quadratic variation of a smooth function is 0. As this is the converse of integral. If you have multivariation, then if you continuous, V2 will be 0. That's it. But it's more or less.
So could you explain again the first term, what is the expectation of the difference to the fourth?
Yeah, this is a result if psi equals n 0 sigma t, the expectation of psi to the 2k is equal to 2k factorial.
Just a computation.
Yeah, it's an induction. It's nothing complicated here. Okay, so now to finish, just remind. Yes. So this is how we will keep on doing this quadratic variation, multivariation, or stochastic integral. But the fact that the drawing motion, so after this is the rest of the proof that I will accept, this uses these two results. But it's very important to just keep in mind that the drawing motion has quadratic variation that is deterministic almost fully. It's given by t. Quadratic variation of the drawing motion up to time t is t. And the volume variation of the body is infinite. So this property here means that we cannot use everything we did for Riemann integrals. The assumption that we had is that to build a Riemann integral, this has to be finite. It's not. We'll do the same thing, but make sense of the bit in a different way, with quadratic variation. Now we start talking about martingales, but I really like martingales. So let's adapt all of this to martingales very quickly. So we take n, martingale, and we write m, the martingale bracket of m is equal to d to m. And what is the definition? The quadratic variation of m is it's just notation for the moment.
So it will define what is this bracket.
This is the definition.
This is the definition. I will explain what the bracket means. We'll just take a notation formula to make it real.
The brackets usually used to put different stuff. Here, how you will use it? Variance.
Okay.
Look, I'm sorry, I was
No, it's very good. Yeah. But now I take n and 2 martingales.
Then you have quadratic form and you want to have like linear, something like that.
Yes.
That's curious. Is it the same process?
Oh, but it's the same as for Hilbert spaces, you actually can define the first norms and define the scalar product.
Thank you very much. Congratulations. Like linear form, quadratic form. But this is just the same.
Yeah, there's nothing different. You can call it scalar product if you want, or scalar product. It's just a bilinear application.
Oh.
Okay, so with this is bilinear and N. The T denotes that I take the integration up to time T. And the first thing that we see is, of course, that W T is equal to it's just a notation. It would make life so much easier for us.
And it's notation only, it's just like calculations.
What do you mean?
But we just calculated it.
This one it's by definition. It's a definition. Because we saw that the periodic variation of W is but by definition. I will use this notation. Come on. So zero. We have a going formula actually, which makes sense. So n up to time t is equal to the limit when the size of the constant y goes to 0 of sum in I n ti I plus 1 minus n ti. I will erase it. I think this is important. Okay, multiply by n ti plus 1 minus n ti. And yeah, this limit you said it doesn't make sense in general. So you can prove, I won't prove it because we'll do everything proper for the prime motion, but not for martingale. This is a limit in probability. This thing exists for martingales. It exists. And martingale bracket is bilinear. And most importantly, nt squared minus n t. So we saw all these properties before. We had Sn squared minus n is a martingale. Wt squared minus t was a martingale. Remember, we did this. We had Wt squared minus t is a martingale. This is exactly this property.
Do you mean this for any stochastic process?
No, for all n martingales. This only exists in martingales. I cannot take the martingale bracket of anything else than martingales. And now I will move a bit further. I will try to give you some insights on what we will prove later, but I want to give you an intuition of what we're going to do. So for this, I need to give you some results that we'll see later. The main result is, of course, so we take nt and martingale. We ask that nt where is bounded in L2, that n0 is equal to 0, then there exists Wt, a Brownian motion such that nt is equal to W of the martingale fracture. So you see here the link between martingales, continuous ones, and Brownian motion. Actually, a martingale, continuous one, in a lot of cases, is just a Brownian motion where you change the speed. Instead of going at speed t, it goes at speed the martingale bracket t. And we'll see much better than this. And that's why we're taking the time to see all these martingales instead of just a Brownian motion. Because it's the same thing, almost. And when we build the stochastic integral, we'll see that this will have an additional term that will appear, the Beetle term, and it will depend on this. And basically everything will be martingales. That's what. That's why we can improve some stuff. Yes, this. I hope so. Yes. But, I need to be able to write integrals, and I am not yet. So I don't do much. I just said in the email that I wanted to talk a little bit about the themes for the exam. So if you want to have an exam, as I said, it's an oral exam at the end, and we'll give you an article to read and just a comment in class to debate about it, I guess. So the first of these projects is a link between martingales and PDs. So we'll just talk quickly about it, and then we'll have all the tools for you to do the exam, the project. It's just a small link. So we'll do something stronger than this. But the point is that if you take u of xt is equal to expectation of phi of x plus w of t. So w is convolution. This is a smooth function. Almost can prove it, right? We have to wait a little bit more. Then you satisfies. It's called in general TC Kolmogorov equation. Du of the TC. Both will have the fashion of these parts. The Kolmogorov equation. That's backward Kolmogorov equation forward in detail. So yeah, let's call it the Kolmogorov equation. We will see some nuances over the course.
Just the heat equation.
Yeah, in this simple context, yes. We'll modify it in all generality because you see the idea here is that we will write this thing will satisfy a differential equation, stochastic differential equation, and then we'll just try and define this thing. It will satisfy SDE, and then we'll take the expectation. One term will disappear because it's a martingale, and we'll end up with this equation with some technical. So, just to talk about the project, an application of this thing that is considered in the literature is to take a box. Let's say 0, 1, and to consider the Dirichlet problem in this box. That's delta u is equal to 0, with u is equal to f on the so this is the box called T. And in T. And you would like to solve this problem, and you can if you use martingales. The idea is the following. You want the solution u of x starting at x. So you start at x, you take the distance between this point and the boundary. Let's say that you divide it by 2. You draw a circle, sorry. You take a point randomly on the circle, let's say here. Then you do it again. You take this circle. Whatever. You take randomly this point, then you do it again. let's say again, and you can prove that at some point it will go very close to the boundary. Then you can just stop. Let's say that you stop at a distance epsilon of the boundary, and you say that the value you obtain is the value on the boundary f evaluated at this point y. You do that a high number of times. You take a lot of these circles, you take the average, and you can prove that doing so gives you the solution to the derivative problem. And of course, it's a very slow method. And you can say that this can easily be solved on a square with finite difference or finite elements or anything. But if you consider a problem in high dimension, or a problem where t is absolutely irregular, this is basically one of the only methods that you have left.
I'm sorry, I'm so far from the middle methods. Okay, you have a point x. How do you u? And you have f on the boundary.
So you have an
algorithm
that gives you a point y of x. This is a random variable that you start at x, and you obtain the point on the boundary, and you take f of this point on the boundary, you take the expectation of that, and this is proven. And yeah, proving that this actually works uses exactly what we've done plus a few other things, not so much. So I think I can stop here. Yeah, if you want more detail, we can talk about it. But that's the first project. Another agenda will also have some projects, and I have another one with numerical simulations of SDEs in a fun way. But just keep in mind for the rest of the work that we'll try to make a link between stochastic integral and some Martingales to see some more general results than this one. And again, to take these kind of quantities where you take the expectation of the function of a stochastic process, and we want to show that it satisfies the PT. So this will be especially useful for us. And I will stop here. This was just a teaser. We will see that from next week with the stochastic integral.
Okay, can you tell once again where it's phi appearing in the equation?
If phi is what?
Where phi appears in the equation.
Yeah, sorry. In strange condition. Just take t on 0. That's what you need.
Doesn't influence the equation, it doesn't appear like in the condition regression.
No. But we will see that it's actually intuition is not that hard. I can't go too fast. Problem says building the stochastic integral will take us some time. Oh, yeah, by the way. Next week we'll begin with the stochastic integral. Then we have the holidays, so there will not be any course.
Holidays?
At the end of February, yeah. The last week of February.
Who told you about this? There is no vacations in Norway until the Easter.
Yeah, I know, but you're not
Children, we won't be here.
You're not married people.
Without daughters, well, you just tell us when you will come and so on. Officially, it's not a vacation. Okay? If people say about vacation, then this is just a cheating.
Wait, vacation was next week or week after?
No, the next week.